Hi everyone. In the previous video, we looked at several situations where we can make use of the empirical rule to determine what is a percentage of certain scores that fall um, under a certain score or above a certain score. But we stopped with a certain problem where the empirical rule seem to um, where we will not be able to make use of the empirical tool. So one of the that's one just one of the reasons why there's a need for us to standardize the normal distribution or to present what we call as a standard normal distribution. But another reason why we need to look at what we call as a standard normal distribution and study it is something that you would realize based on this next example. So we will park the question first regarding Jasper's score, and we will consider two other people, April and May, in a different context. Now, April and May are twins who go to two different schools, two same schools, but belong to two different sections. Let me repeat that. April and May are twins who go to the same school but belong to two different sections. After the third quarter, April obtained a grade of 87 in statistics and probability, while May got 88 in the same subject. When their parents asked April why she got a lower grade than her sister, April reasoned out that she actually got a better grade than May. So now the question is, which is something that I want you to take time to think about, is how is that even possible? How is it? How does April make sense, or how does she um, defend why she believes that her grade of 87 is actually better than May's grade of 88? So while you think about it, I'd like you to pause the video here and play it again or continue with the rest of it once you feel that you have decided what are the possible reasons that April can use to defend her case. All right. Now, if you're thinking that it's actually important to take a look at the grades of the other students in the same class as April and me, you're actually on the right track. Let's take a look at some of the grades that all of the students in April's class obtained. So we see that there are 18 students in April's class, and she was able to obtain a grade of 87. On the other hand, in May's class, which is a different section going through a similar subject, she was able to get a grade of 88. But what is it that you notice when you compare the distribution of the grades in both April and May's classes? When we consider how April's grade compares with the rest of her classmates, it's easy to see that she performed better than most in the class. May's grade may actually be higher. 88 is definitely higher than 87. But in comparison to the others in her class, May's grade may not be as impressive. So, what's the moral of the story here? When we try to compare two different scores coming from the same distribution, then we can just make use of their values, to make a comparison. For example, if April and May are in the same classes and they obtain 87 and 88 respectively, then definitely we can make a comparison between the 87 and 88 and just simply say that May did better than April. However, since these two girls are coming from two different scores and their scores are coming from two different distributions, it's necessary that we also take a look at the context at where their grades are coming from. So the 87, when you take a look at the distribution of scores in April's class, is actually quite a good score. If you notice, she is even the second. She even got the second highest grade after 89. On the other hand, in May's class, she got a grade of 88, which is actually higher than 87, but 88 in comparison with the other students in her class is not as impressive. So there are many factors that would come into play why this happened. Possibly they may have different teachers, or they had to work with two different projects that vary in difficulty and so on and so forth. But at the end of the day, when we put aside all of those factors, what we're truly interested in is if these two scores are comparable, how do we find a way to compare the 87 and the 88 so that it's more obvious that the 87 is actually a better score than the 88. So this is where the idea of standardizing scores come in. Standard scores are also called as z-scores. And the reason why we standardize scores is because it allows us to compare two or more scores that are from different normal distributions by converting scores in a normal distribution to z-scores in what becomes a standard normal distribution. So what we're saying here is there is a way to compare the score from one distribution to the score in another distribution, of course, with the assumption that we're working with the same kind of continuous random variables, and with the assumption that both of these distributions are normal. So those are the underlying assumptions. How do we compute for the z-score, or how do we convert the z-score, the standard, sorry, how do we convert the actual score in the distribution into its corresponding z-score? And that's what we're going to present here. We can make use of the formula z is equal to x minus mu over sigma to transform or to convert an actual observation or an observed value into its corresponding standard score. So z would represent the standard score, x would represent the observed value, mu represents the mean of the distribution, and sigma represents the standard deviation of the normal distribution. All right. So if we take a look at it, using this the formula, if we make use of the value of the mean and as an observed value, and substitute this to the formula, you would have mu, or mean minus the mean in the numerator, divided by some value sigma. But because the numerator is 0, that means that the standard score for the mean would be equal to 0. And for all of the other points along the x-axis that correspond to +1 and negative standard deviations away from the mean, we make use of the integer. So if the mean is 0, one standard deviation away from the mean to going to the right is going to be 1. Two standard deviations would be 2. Three standard deviations would be 3. And going to the left, we would see -1, -2, and -3. That's because in what we call as a standard normal distribution or a standard normal density curve, such as the one that we now see, a z-score tells us how many standard deviations a value is above or below the mean. And the mean in a standard normal distribution is equal to 0, and the standard deviation is equal to 1. So when we convert an observed value into its z-score, what we're actually finding is a certain value that corresponds to exactly how many standard deviations is that score away from the mean. And to better understand this, let's take a look back at April and May's grades in their classes. I will not be asking you to compute for the mean and the standard deviation for each of those two classes. That's reserved for a previous topic. But if you want to double check, you can do that before proceeding by pausing on this part of the video. However, we already see that the mean has been computed for us for both of the classes as well as the standard deviation. So let us make use of these values to convert April and May's grades into their corresponding z-scores. So let's begin with April's grade of 87. Since the mean is 81 and the standard deviation is 3.83, we plug those values into the formula, and we should be able to find that the value of z is equal to 1.57. So that means that April's grade of 87 is 1.57 standard deviations away from the mean. On the other hand, when we do the same process with May's grade of 88, but with the mean of 89 and the standard deviation of 3.30 in her class, we see that her standard score, or her z-score, is negative 0.30. And you know, when we encounter negative z values, that means that the score is actually to the left of the mean. So this means that May's grade of 88 is negative 0.30 standard deviations from the mean. So it's to the left of the mean. Okay, so this is what, again, like I said, what we call as the standard normal curve. The mean is 0 and the standard deviation is equal to 1. So for example, if we want to compare April's score and May's score, we can locate them along the x-axis and draw vertical lines to represent portions of the normal curve. And we notice that the 87 and the 88 now correspond to 1.57 and negative 0.30. So in this manner, when we try to compare April and May's grade in statistics and probability, it's now easier to see why April's grade is actually greater or better than May's grade, because we see that April's Z-score of 1.57 is better than negative 0.30. What this also tells us is, if we consider the area to the left of each of these scores, which represents how many percent of the class actually has a smaller or a lesser grade than May, we notice that the area to the left of May's score is much significantly smaller than the area to the left of April's score. So that's another way of comparing the two values. But let's take note of the notation that we use. We can represent this by using P, or the probability, or the percentage that Z is less than negative 0.30. And this represents the area of the normal curve to the left of May's Z-score. Another way of looking at this is it's the probability that another student has a lower grade than me. Of course, the same interpretation, a similar interpretation would apply for the probability of Z being less than 1.57. All right, so let's go back to this problem. Now that we understand why there's a need for us to study the standard normal distribution, we need to go back to applying what we already know about the Z-score into the problem that we stopped with in the second video. We will continue this discussion with the next one.